get started, I have a word from our sponsor. And this is specifically directed to astronomers and information scientists who might like to work with astronomers in 5 minutes. And that's that NASA is currently undergoing, so actually let me preface this. Okay, I cast this as an advertisement, but if you walk away with one thing from this talk, especially if you're in that audience of astronomers or information scientists who want to collaborate with astronomers, this is the thing you should walk away with, because I think this is very important. I hope you'll find something interesting in the science that I'll talk about, but this will influence the future of our field. So NASA is currently undergoing a review of its research programs that fund individual investigators, guest investigators. This kind of thing happens about once per decade. And I'm on a panel of astronomers that are advising them, not so much with the actual review of existing programs, but establishing metrics for them. But they're seeking input from the public on what people think of the current state of the program, the way it's been changing over time, and the way they think it should change. And let me just point out that our field of kind of interdisciplinary work that focuses on methodological research has not fared well in the previous reviews. And the consequences of that are, in the last few years, some major programs that have funded our work have died. And if you're unhappy with that, this is your opportunity to say something about it to people who are equal here. So I'll show this slide again at the end, in case you want to jot it down. But just Google NASA Astrophysics Program Review. Follow this URL to make your comments. All right, so now, I hate to talk about money and stuff, but that keeps us all doing the fun stuff. And so let's start talking about the fun stuff. So thanks to our friends at Google, this is from the sky view of Google Earth. I have a map here of what the night sky looks like at about 9 o'clock looking to the northwest. Of course, you probably won't see most of these stars over Manhattan, but some from elsewhere will hopefully see them. And I chose this particular direction and view for a reason, even for people who don't know the night sky that well. Hopefully you at least know the Big Dipper, which is this asterism or pattern of stars in the Big Bear constellation. So it's upside down here. And you may know this trick that if you follow the two stars at the end of the Big Dipper, you'll reach the pole star, Polaris, and the Little Dipper. What I'd like you to do is go a little bit farther to the next kind of visible star. It's just a little dimmer than the pole star. It's called Gamma Cepheus. This kind of house-shaped constellation. This view here, these new symbols, these ellipses, show extrasolar planetary systems that we now know. And so I directed you here because this is probably the easiest one to find in the northern hemisphere. So I want you to be able to tell your friends when you walk out at night, be able to point to them, an extrasolar planetary system that we now know of. The other reason I chose this map, John's really excellent talk kind of set up for this, is that down at the bottom here, so right at the horizon at about 9 o'clock, is the constellation Cygnus, the Northern Cross. It's very easy to find. And as you heard earlier, the field of view of Kepler is in the Northern Cross. In fact, in the summer, if you look straight up in the late evening, there'll be a really bright star, Vega. That's very easy to find. It'll be the brightest star overhead. And again, you can point to your friends. As John said, you can hold out your hand and you can say, hold it up next to Vega and say, we now know of 1,000 solar systems right there, which I think is just remarkable. That's just such exciting stuff that Kepler is doing there. So as was mentioned, those are our candidate solar systems, and astronomers need to do some expensive observations to follow up on those and confirm them. This shows some of them classified by size, but since John talked about Kepler. So what I want to talk about today is how one would go about kind of trying to optimize the use of resources to do the kinds of follow-up required to do confirmation. And it's kind of a little bit of a semi-philosophical background. I'm from Cornell, so I'm going to include a Carl Sagan quote. I like this quote. I use it start my classes on Bayesian statistics at the summer schools and astrostatistics that are held in Penn State each summer. And so Carl has this kind of provocative comment: science is more than a body of knowledge, it's a way of thinking. The method of science, as stodgy and grumpy as it may seem, is far more important than the findings of science. And one reason I like to use that to start my course is that I think of statistics and the information sciences as kind of the part of the scientific method that we can describe quantitatively with some kind of mathematical precision. So I like to try to convince them that people who do this kind of research are kind of doing research in the scientific method, not just in astronomy or particular discipline. Kind of the school book description of the scientific method that we get is based on what's sometimes called the hypothetical deductive approach. The idea is that you form a hypothesis based on past knowledge or some theory, then you devise an experiment, some kind of monolithic set of observations or tests. You perform it, and then you do analysis, and then you iterate this procedure. What this talk is about is trying to build within the experiments step the iteration. And so one of my colleagues came up with the term Bayesian adaptive exploration for this kind of framework. And this is just a very crude kind of flowchart cartoon of the idea. The idea is you have some strategy for doing observations and prior information perhaps from your existing data. And then you implement those observations and you get new data. And then you make inferences based on that new data. Then you make predictions that you use to guide the design of your next observation based on what you've learned from the data. And the idea is to do this online. So it's related to active learning and things like that. But the new piece is that it will be done in a kind of astrophysical and nonlinear model context. So with that as kind of the teaser introduction, here's my agenda. So I'll describe some of what's already been described about discovering exoplanets with radial velocity observations. Then the bulk of the talk will be, I'll try to explain in kind of big picture terms the theory that underlies this Bayesian adaptive exploration idea. I have a toy problem with some simulated data that's very simple and cartoonish, but if you can see how things work. I think I'm not going to have time to go through it, but we'll see if I do. We'll do that. But the main thing I want to get to is at the end I'll show you it in operation for data with actual real data from an exoplanetary system. All right, so first, just the astronomical background. John's talk focused on this transit technique that the Kepler mission is using, where you watch a planet pass in front of its host star. Most of the existing confirmed planets, of which there are about 500, were detected by looking at the reflex motion of the host star. So the key idea behind it is that all the bodies in a planetary system orbit. They orbit with respect to the center of mass of the whole system. So we like to tell our students in elementary school that the planets orbit the sun. But really the simplest description of the solar system's motion is that all the members of the solar system, including the sun, orbit the center of mass of the solar system. So in particular, if you were an observer 30 light years above the plane of our solar system, looking down at it from 30 light years away, you would have seen over the past few decades the sun do this kind of complex wobbling dance on the sky. And the axes here span plus or minus 1,000 microarcseconds, or a milliarcsecond. So a milliarcsecond, remember an arcsecond is a 3600th of a degree, right? So this is a very small motion. Most of this motion is due to Jupiter and Saturn's tug on the sun. The component of it due to the Earth is 1/1000th of the scale of this plot. But the point of this is that the host star of our solar system and of other solar systems moves. This is a plot of the side-to-side wobble, but there's also motion along the line of sight if the plane is tipped. And the radial velocity method tries to detect that along the line of sight motion as a measured velocity measured via Doppler shift. So when the host star moves towards us, spectral lines are blue shifted. When it moves away, they're red shifted. this is what the raw data, so to speak, look like. They're spectra with thousands of lines. This is in a shell spectra where there are different borders, spectral borders that correspond to different color. The color scheme is laid on afterwards. Many of these lines are actually calibration lines from an iodine or other cell that's placed in front, so you know exactly where lines should lay. And with so many lines, it's capable, and this is a very impressive technological feat, it's possible to measure the locations of the line centers to 1,000th of the width of a spectral pixel. And that's astronomers, the astronomers who do this, measure the speeds of objects that are tens of light years away with this kind of velocity, so walking speed, meters per second, of things that are hundreds of trillions of miles away. It's just an amazing technical accomplishment. So the reduced data that people like me get after a very non-trivial analysis of this are velocities as a function of time. And that's the kind of, at the level that I want to talk about, think of things as measurements of velocity as a function of time. The times are irregularly spaced. And though it's not evident to the eye, in fact, there's a periodic signaling here. Not a sinusoid, but a periodic. So when you get data like those velocity time series, there's many statistical tasks you like to do. You like to detect planets. You want to see if there's a periodic signal present, or if there's more than one present. Once you've detected them, you'd like to estimate the orbits, so measure periods, eccentricities, tilts of orbits. Once you have a system well characterized, you'd like to predict orbits in the future. For example, if there ever is a terrestrial planet finder, we'll want to predict when are good times to observe particular systems. Or for ground-based transit observations, you'd like to predict when transit will happen. When you've looked at many systems, most of the astrophysics actually lies not in looking at individual systems, but looking at the population level and trying to see correlations of things that tell you about the planet formation process and stuff like that. So this is actually a problem I'm really going to use. What I'm going to focus on today is optimal scheduling, which is related to all these things, especially to prediction. How can you use limited and expensive resources to address all of these goals by picking observations that will give you the most information? And one of the nice things about addressing all of these tasks within a Bayesian framework is that this all gets kind of integrated. They're not all separate problems. You have to do this to do this, and you can use the output of that directly and straightforwardly to do this and this. So that's why we've chosen that approach. So let me tell you about this Bayesian adaptive exploration idea. So the basic idea is to talk about designing an experiment or a sequence of observations, thinking of that as a decision theory problem. So whenever we perform an experiment, we have choices of actions to actually do, things we're going to actually do, behaviors we're going to have, what sample size to use, what times or locations in space to probe, things like that. And we have to make our choices about the properties of the experiment amidst uncertainty about what the data will be like and what nature is like underneath that data. And so we'd like to do this in some kind of principled way that will account for all these kinds of uncertainties. Bayesian decision theory is a kind of a general approach for making decisions of any type in the light of uncertainty. And the key idea behind it, the key additional piece to what most astronomers know about Bayesian statistics, which is this idea of likelihoods and priors, the key new piece in decision theory is that decisions depend not just on what you know about the system, but on the consequences of your actions. So the classic example is Russian roulette. If I were to hand you a 6-shooter that has one bullet in it, spin the chamber, and offer you $100, to point it at your head and pull the trigger, you will not act as if the most probable hypothesis is true, right? The most probable hypothesis, by odds of 5 to 1, is that the current chamber is empty. But I think you'd all agree it would be a fool who would take the $100. Right? So the decision you make is not to act as if the most probable hypothesis is true. Something about the consequences of your of your actions factors into making decisions. Decisions aren't just about uncertainty, but about consequences. So to deal with that, decision theory introduces these ideas of utility or loss functions. So you compare consequences via a utility that gives you the benefits. It has to be some kind of scale or quantitative measure that gives you the benefits of a decision, or a loss quantifying its cost. So this is a function of the actions you'll decide and what the outcome is. So action would be, whether I choose to pull the trigger or not, accept the bet or not, and the outcome would be, bang or silence. Of course, the outcome is a little more serious than noise. And then that's kind of the optimistic approach to decision theory. The pessimist might phrase things in terms of a loss. And so to do this, if you were to phrase the Russian roulette problem in decision theoretical terms, you'd have to assign, maybe, if I offered you $100, you'd have to kind of come up with some monetary value for your life to assign as the utility that, or the loss you would incur if you were killed. And presumably that's large enough that it overweighs the fact that a bullet being present has a lower probability. All right, so we're uncertain of what the outcome will be. So how do you make a decision between the different, pick one place in the action space. So the idea is that you average over the possible outcomes, weighting them by their uncertainty. So here's the utility function, whether to accept the bet or not, and then what the Leisure will actually hand me in the gun. I don't know what that'll be, what those outcomes will be, so I take what I know, calculate a probability for them, and then marginalize that out. This thing is called the expected utility, and the best decision is the one that maximizes that. And there's a kind of axiomatic theory about this. It has some kind of conditions on what utility functions look like and stuff like that. But there is a kind of axiomatic basis. So Bayesian experimental design is to phrase the choice of experiments as a decision problem in this Bayesian decision theory. So the actions are just, the action space would just be labels for possible experiments, like choice of a sample size n, or choice of the time to take my next exoplanet RV observation t. So I'll label my experiments by some labels. So the outcomes that I'm uncertain about are what nature will hand me in terms of data from that experiment. I don't know what data I'll get. The utility will measure the value of a particular data for achieving the goals of an experiment. And it might take into account the cost of an experiment. It might be more costly to observe at certain times than others. It might be more costly to observe during dark time than light time, or things like that. Yes?
Cost and losses.
You can talk about it in terms of, cost could be losses that appear as a negative in the utility. Or you could frame it in terms of losses. In fact, I'm not going to talk about cost. I'm just going to focus on other terms of this. So the idea is you choose the experiment that maximizes the expected utility. So the outcome space is the data that might arise. And what we need to do this calculation is the predictive probability for the data as a function of what experiments we choose. Now, to predict the data, we're going to have to consider various hypotheses for the data producing process, like what is the true orbit of a planet? We don't know. We have to take that uncertainty into account. So to do this, to evaluate this probability, I'm going to introduce the unknown state of nature, h, and then marginalize over that. So I have a sum over data to get my expectation of the utility, and then I'm going to have to sum over the hypothesis space to get the predicted probability. So there's a hint of trouble ahead. I've highlighted in red those sum signs that in a continuous space where we usually live, these are integrals. And they are probably, in most cases, sometimes this might be one-dimensional, but almost always this is multiple dimensional. So we have to integrate. We have all the problems of doing a normal Bayesian calculation, which involves integrals over hypothesis space. But then we also have the problems of doing a good frequentist calculation, which involves integrals over the sample space. So it's kind of, computationally, it's the worst of both worlds. And then in addition, we have to do an optimization over the space. So the theory I'm going to tell you about actually has existed for about 70 years, but it's only in the last decade or so that people have been able to apply it to nonlinear models of realistic complexities, and that's why you're hearing about it now again. So what utility should we use? So in particular for exoplanet observation. So a lot of scientific studies don't have a single clear-cut goal that would let us kind of try to come up with a particular cost. Like we want to know the period, and we want its accuracy to be so and so. Usually, the kinds of experiments we do in astronomy, we have a kind of a broad goal. We just want to learn and explore, and the information we discover will be used for lots of different purposes by different scientists. So, for exoplanets, you might use them for the characterization of a planet to infer the mass of the planet or whether it's in a habitable zone. Or you might be interested at the population level, or you might want the information to plan, the TPF follow-up. So we're going to try to use a general purpose utility, and for that we turn to information theory. And we're going to measure the information gain provided by new data as a change in entropy. And I'm going to talk here in terms of Shannon entropy. Kind of the more formally correct thing is to use Kullback-Leibler divergence, or Shannon entropy with a measure in it. But this, the answers actually don't change because of the averaging. So when you just talk about the simpler case, so the Shannon entropy, just to remind you, it's a scalar measure of the degree of uncertainty expressed in a probability distribution. And one way to kind of intuitively motivate it is it's an average, so a probability weighted sum of something that some people have called the surprise. So just this term here, the log 1 over p. If p is small, then this thing is big. So if you see an outcome I when p is small, that's a surprise. That's why this thing is called a surprise. So a very flat distribution with many options, all the p's would be very small, and the average surprise would be very large. So flat distributions have large entropy. So do the log, it's minus p log p. So that's what the minus. So for a measure of information gain, we imagine we have some existing data, big P, and we can calculate our current posterior distribution. And if we get some future data, little d, that will presumably shrink our posterior, and we'll measure the information gain from that data as the entropy that we started with minus the entropy that we end up with, which should be smaller. So this number will be positive when we gain information. So this is a sum of p log p in the updated posterior, the little d there, and minus a constant term, this thing here. So minus s, so there's now this goes away, and we have a plus sum. So this, as I mentioned, this was first advocated over half a century ago. Just to make a connection to some things you might already appreciate, the entropy of a Gaussian distribution, or in this case the information, so the negative entropy, is minus log of the standard deviation. So a larger standard deviation is a larger entropy for a lower amount of information, negative. And the multiple dimensions is just the determinant of the covariance matrix. But it's not a measure of variance or covariance. So for example, these two distributions, this one has a much higher variance than this one, but they have the same entropy. Right? The entropy measures kind of the size of the regions that have probability, not some kind of metric. We're going to use as our utility the information gain provided by a datum at the new time. So it's just if I update my posterior distribution with the new datum, and then calculate the entropy in the updated posterior, that's the entropy. So when we were talking at the very beginning, with that D is the outcome, we don't know what data nature will hand us, so we have to average over values of D. So we get an expected information. This is our expected utility. So that's the integral of this thing, this information, times the predictive distribution. And that predictive distribution is itself a sum over, over the hypothesis. So we have to take into account the uncertainty in the orbit, for example, to make predictions about the future. So there's, as I said, there's a heck of a lot of averaging going on, and actually most of the time I've spent on this project is on doing those averaging, and I'm going to spend very little time, just the next 2 slides, telling you about that research, because it's kind of grungy, but that's actually where the work is. So there's just a couple key ideas I want to communicate on these slides about the computation. So let's imagine that I've detected a planet, and I just want to estimate the parameters of that planet's orbit. So I'm in a parameter estimation setting, not the detection problem, but the parameter estimation. So I have some model that there's a planet present, and it has some unknown parameters, theta, the period of the orbit, the size of the orbit, its eccentricity, and so on. And I have some current data, and that gives me a current posterior distribution, of contours in that space, or points in that space. And then the expected, so I'm going to make one further assumption, and that's that the entropy of the noise distribution, the width of my noise distribution at a given time, doesn't depend on theta, on the parameters of the planet's orbit, which is reasonable. A few lines of algebra, just kind of using Bayes' theorem and an information theory identity. You can show that the expected information at a future time is some constant times this integral here. And keep its minus sign and look at what this integral is. So it's an integral of my predictive distribution for the data at the future time times the log of that predictive. So this thing here, including the minus sign, this is the entropy of my predictions at a given time. So remember, entropy gets big when your distribution is uncertain. So this is saying the best observing time, the time that maximizes this, is the time for which my predictions are the worst. So it's kind of an intuitively sensible criterion to learn the most, sample where you know the least. So, but how do I actually calculate that integral? So I rewrote it here. So we use a nested Monte Carlo method. So we're going to do standard tools for Bayesian inference to get parameter distribution, samples in parameter space by Markov and Monte Carlo, say. And then if we know those, then we can both evaluate and sample this predictive distribution with very straightforward kind of Monte Carlo methods. So that's this nested Monte Carlo integration. And then to do this posterior, to get these parameters, this sampling in posterior of the posterior distribution, we're going to use a property of these exoplanet models, which is that if you write out the model, it's a linear sum of nonlinear terms. And you can do the linear part analytically, so you can reduce the dimensionality of the model. So we separate our variables into a fast set that we can handle very easily, and then a slow set where we actually have to do careful MCMC. And we do that using some fairly modern population-based adaptive Markov-Chain Monte Carlo. The one we're using most right now is called differential evolution MCMC. So I think I do have time to go through this toy problem. So let me just show you it at work on a very kind of silly toy problem. But yeah, you can kind of see what the method is trying to do, and it looks somewhat intelligent. So let me go through it. So here, the setup is that I'm looking in space for some bump. I'm going to make some measurements at different places in space, and I'm trying to detect some signal that should look like a Gaussian-shaped bump. And I don't know the location or the height or the width of the bump. And so here's the unknown true values of the location, the full width half max, and the amplitude. And I'm going to do a scan with an instrument that would give me a signal to noise measurement of 5 if I were right on top of the peak. And here's the unknown true object, and here are 11 initial data points. So most of them are too far from the object to do anything. There's really only one that has any substantial signal, but there's a little bit of constraint to this one. And then I'm going to ask, where should I observe next? So I'm going to go through that each step of that Bayesian adaptive exploration cycle. So there was the observation step that I just did, then there's the interim inferences, and then there's the design step. And I'm going to go through a couple of cycles. So we just got observations. Now we're going to have to do interim inferences. So we're going to do the kind of standard Bayesian thing where we'll use posterior sampling. So Bayesian inference gives you a probability for your parameters. So probability for the location, the width, and the amplitude. And I just create a pseudo-random number generator that will give me points in that 3D space. And so here's a set of points, two-dimensional marginals. So location and amplitude, and location and width. Just to give you a sense of what's going on there. And there's a hint here, and you'll see more about it later, that there's things are definitely not Gaussian. There's kind of this little clump out here. But I should mention that in the limit where you're dealing with linear models, you can do, even though there's all these layers of integrals and sums, you can do them analytically. So there's a huge literature on this linear case. But part of the reason I'm pointing out the kind of non-Gaussianity here is I'm interested in what happens when all that linear stuff can't go down. So here's a plot that I really want we'll spend a minute describing, because you're going to see a few of them. So there's one abscissa of the location, so choices of the next observation, and there's two vertical axes, coordinates. So these actually the thick dashed curve is the unknown true Gaussian, right? It was located around 5 and it had a width of order 1. These thin curves here are, I took the points that I showed you here, for 15 of these points, I just plotted their curves, plotted the Gaussian bump that corresponds to just 15 of the points. So these thin black curves are meant to be a visual depiction to you of the uncertainty in my prediction of what data I would get if I observe at a given point. The green curve, which is the one curve that you read against the right axis, is the entropy in the predictive distribution, and it basically follows what your eye would guess from the distribution of the black curves, where their widest is where this thing tends to peak. So the black curves are kind of a picture of the predictive distribution, and the green curve is its entropy. So max end sampling says the next best observing time is at this time right around 5. So we simulated a new observation, and we get new interim inferences. And as a crude measure of volume, you could just look at the product of the standard deviations in the 3 directions. And with this one new observation, it's shrunk by a factor of, I forget what it was about 5 or 6. Which isn't too surprising, because you really only had one data. We started with 11 observations, but there were really only 1 or 2 there. But the point is, you can see really what a non-Gaussian or non-linear problem this is. The posterior is nothing like normal. And you can kind of see what's going on by looking again at the predictive distribution here. Our new observation, which was right near where the center roughly is. So the observation was here, the center's here. It's basically pinned down the curve here, but curves can exist on both sides of that point and with various widths. And that's what causes this kind of horseshoe shape in the posterior distribution. So now the entropy curve is this green curve, and it has this interesting structure. It says you don't want to observe anywhere near where you just observed, but you want to observe a little bit to either side to start now constraining, instead of the amplitude, the width. And it's slightly better to look on the left, so we do that. And we get another shrinkage by a factor of about 4 in the parameter space. And now it kind of automatically switches to looking on the right. And you do that point, and you get another factor of about 3. If instead of looking at this point, I looked at a point around here, I would have instead got these inferences, which actually have considerably more volume. The points are all overlapping. It's about 2 or 3 times larger volume. And they're also, you see that the correlations were highly reduced by using the alpha model. So that was just a kind of toy problem where you could see that it's kind of doing the smart thing. It's that it figures out on its own that, okay, first I want to try to find the peak. And then once I've nailed that down, to kind of bound it on So now let me show you an exoplanet example. Again, I'm going to run through this three-step cycle a few times. And I'm going to use real data. So the problem with using real data is that you don't know what the truth is. So I'll fudge around that in a way that I'll explain. So here's the real data I'm using. So in 2000, Voda et al. Reported observations, 24 radial velocity observations of this star from the Henry Draper catalog. It's a star much like the sun, about 120 light years away, reasonably bright. And so here's its velocity versus time. This is time in days, so this is over a period of a few years. So the error bars are about the size of the symbols. That's why you don't see error bars. They're actually plotted, but they're designed. So clearly there's something here. And I'm going to treat this as a parameter estimation problem. They've already done the analysis. They're convinced there's a planet. This actually looks a lot like a velocity curve for an elliptical orbit. But I want to say, okay, what's the best time to observe to learn the orbital parameters better? All right, so this is just to remind you what the parameters are for interplanetary orbit. If you're just interested in the line of sight velocity, there's an orbital period, there's an orbital eccentricity, there's an amplitude that's related to the size of the orbit. That's just the amplitude of that velocity curve. And then there are some geometric parameters involving the tilt of the orbit and its orientation, as well as kind of just the overall velocity that the whole system is moving. So the blue ones, the ones highlighted in blue, are the slow variables. They're the ones that appear non-linearly that I can't handle analytically. So it's the period, the eccentricity, and this kind of orientation of the orbit parameter called the mean anomaly. This is an angle. And to make predictions for a given choice of those, you have to solve a very famous nonlinear equation. Easy to solve, a famous, very strongly nonlinear equation called Kepler's equation. So it's a strongly nonlinear model. The likelihood function is highly multimodal. It's very, very much of a mess. So here I'm showing you output from the MCMC for the inferences, posterior inferences from that initially published data set of 24 observations. So this is kind of the standard MCMC scatter plot. So it's just pairwise marginal distributions and then univariate marginal. So this is for period, this is the marginal distribution for the unknown period. This is about 55 days wide at about 600 days. And so period, eccentricity, and then that angular variable, the mean anomaly. And so there are strong correlations. There are things that break any kind of Gaussian approximation for the eccentricity. Physically can't be above 1. And very typically you see likelihood functions or chi-squared surfaces that peak or are large at that limit. At one limit or the other, 0, a circular orbit, or 1. So things that involve Gaussians kind of break down. All right, so here's another one of those design plots. I'm going to spend a few times blowing up this and expanding this. So here's this black curve is the best fit that was reported, which is also the Bayesian map or maximum a posteriori estimate. Here's that black curve. The blue curves are, again, this time I took 20 points from here, and I plotted their velocity curves. So those are kind of the predictive distribution, a picture of the predictive distribution. And you already see one interesting thing, which is the point that for nonlinear models, the map estimate can actually be very atypical of where the posterior probability lies. So the map is an orbit with a fairly low velocity amplitude of a couple hundred. But the typical orbits in the posterior distribution have velocities that are much higher. So it's just a caution that when you're in non-linear models, which was not the Kepler case, that you should be aware of map estimators. And then the green curve again is entropy versus time, measured as bits of information gain, measured as if versus repeating the last measurement. And so there's this nice big peak here of many bits, 5 bits. Remember, a bit means shrinking your volume by a factor of 2. So that's a huge information from a single observation. Now let me blow up that last region. with the magenta points, at a few times, I've plotted actually all the orbits instead of just the 20. So you can see some of the structure and the predicted distribution. The point being that the predicted distributions are also very non-normal. Some of them are bimodal. They typically are very skewed. So this is just a problem that you don't want to do with the kind of existing linear model methods. I also calculated the entropy curve out to the distant future, just to show you that it kind of does a sensible thing. Right? As you go far enough into the future that your phase uncertainty, your orbital period uncertainty makes you lose phase, then there starts to become no time to be preferred over any other time. And so you can see the peaks in the entropy curve are shrinking, kind of approaching something constant. Actually, I think it's non-trivial what will happen later, but I haven't calculated. All right, so a few years ago, that same team went back and re-observed this system, and they got 13 new points. So I've plotted, based on the earlier observations, the predictions and the entropy curve. So that's the predictions are the velocity versus time, and the entropy curve in green. And the red dots are the new data points. The lines just show the times. So you can see the majority of them were at times that actually weren't very informative, though there were a few that happened to be at pretty informative times, 1, 2, and this one also. So we don't know what the truth is for this system, but so here's the game I'll play to try to just get some sense of whether BAE, this adaptive exploration, would have had something to offer. I'm going to use the best fit that they recorded at the end, using all 13 new observations. I'm just going to consider that to be the truth for the purposes of simulating other observations that might have been taken. So what I'm going to do is, one at a time for 3 cycles, I'm going to take new simulated observations from the best fit and see what would have happened if you stuck to the optimal time. So the next optimal time will be here. The next one won't be here because I'm going to update with the information I gained from that observation. I'll get a new green curve. It'll probably be somewhere close to there. And I'm going to iterate that a few times over next to the end. So here's my what I showed you earlier, the starting point. We'll take a new observation, and here's from one new optimal observation, that's how much things shrink. So the product of the standard deviations is reduced by a factor of 2.5 from one new observation added to 24. And some really kind of complex structures actually here, bimodal. So we're going to do it again. We'll take another further observation. Things shrink again quite a bit. The product of standard deviations shrinks by 1.5 times. And then the third one, and I don't have an intuitive explanation why this suddenly happens. It actually, in some simulations, this doesn't always happen. But for this case, that happened to be the first one we ran with real data. The third optimal observation shrinks the uncertainties by a factor of 30, with one additionally optimally planned observation. And so I'll compare this with the Bayesian inference, the full posterior, if you look at all the observations. And the point is, from those 3 optimally chosen observations, you could have gotten a posterior that was 7 times smaller in volume than the one found with the 13 non-optimally chosen observations. And this is the only case we've done. This was just the first one we've chosen. So I have no idea how typical these numbers are, except to say that in simulations, simulated data, they're not too similar. So that's my story. I just want to summarize with a bit of outlook on what the open issues are and the ongoing work in this is. Part of our reason of trying to do this fast, slow variable separation and use advanced NCMC techniques is because we want to get into more complex scenarios dealing with multiple planets where there are more parameters, so you really need to have a better posterior exploration. And we also want to handle the case where there are the majority of stars do not have detected planets, and we'd like to quantify what we know about them. Are we sure that there's no planet there, of a given mass, or how probable is it? So we'd like to do a full Bayesian calculation when there's marginal data. That means those cases are cases with lots of important modes, and so it's hard to do those. We're exploring C algorithms. I showed you an example where we were doing parameter estimation. We'd also like to do this adaptive exploration when we don't even know if there's a planet there. It turns out that's actually where we've spent most of our time, and we don't have a working solution to it yet. It's a much harder problem. So we have come up with a total entropy criterion that kind of smoothly moves between trying to optimize to detect, and then once the evidence builds up on a one planet or a two planet model, it kind of smoothly shifts over to the parameter estimation case that I already described for you. But the problem is there's two kind of computational hurdles. The first is that Maxent sampler that I showed you, which I should have mentioned, removed a layer of integration, that is no longer valid. So we get a whole other set of dimensions we have to integrate over. And then this involves these integrals, these things called marginal likelihoods in Bayesian calculation, integrals over the whole parameter space. The normalization constant for the posterior actually appears when you do this planet detection case. And those are hard to compute. That's actually where we spend a lot of time. And then finally, I showed you a greedy design where I always asked, what's the one next best observation? And there's no theory for this, but what's known about model comparison is that usually non-greedy designs where you jointly plan multiple observations tend to do better. And I don't know of any intuitive explanation for that. So just in closing, I want to mention my collaborators. So David Chernoff, a fellow astronomer at Cornell, is the one who got me interested in this problem, and we've worked on it together. And this has been collaborative work with statisticians at Duke, Merle Spide and Jim Berger, and two postdocs who've done really good work, especially on marginal likelihood computation. And that's my story, and let me just close again with the most important thing to walk away with. Please say something to NASA if you want methodological research to be funded. Say something to them. Thank you. I can just be available for questions later. So take questions.
So I guess to some extent what we're trying to do here is build a better Jeff Marcy or a better Paul Butler or what have you, one of these people who does this. But you're posing questions that aren't the questions that they need to answer. I have some insight into this just because my wife, 95 is doing this exact thing with Jeff Marcy. And when they do this, of course, what they have is height and stars coming up and down and the rest of stars and so forth. And so what the choices they're really making are is given the nights that I have, I guess you can step back and say, given the amount of time I have in my life for applying for time telescopes, blah, 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 right? If that's a part of it. But assume that you have 5 nights coming up. What do you look at?
Right.
Not, I want to know the answer to this one question. When do I, comment to your cat?
It's a very good point. So let me say 2 things about it. So the first thing is that actually what started our research on this is that Dave and I both were affiliated with the SIM mission, the Space Interferometry mission. This was a mission planned to look at the side-to-side waffle. And so that was a telescopic mission, which would have been in exactly this kind of scenario. So they could choose any time to observe any system. So that was the motivation, the initial motivation for this work. But even in that setting, to make a decision of what to observe when, it's not just a matter of how much information you learn. There's all kinds of other costs. In this field, you could observe 5 objects, but in this field, only 2, right? So there's all kinds of things to play off. So we're just thinking of this as one ingredient, an objective ingredient that the observers should be able to straightforwardly calculate for the task to look at. So in fact, Jeff and Deborah are very interested in this work. At Cornell and talking with them about it. What they'd like would be a set of these entropy curves for all their objects, so that on a particular night they can decide, okay, which are the ones that are most informative to see tonight, given the times that I have. Or people like Josh and Wynn would like me to do an entropy curve for what's the best time for a transit observation. So there are ways to tackle those problems, but your point is that the utility function is actually way more complicated than the information being one observation of one system. And that's absolutely right. Yeah, Kurt?
Besides your last a couple things I came away with. Get back to that last question, which was actually interesting. Corollary to that one. But I was thinking about your Russian roulette
Well, actually, so there's actually people who, as you might imagine, decision theory plays a much more prominent role in econometrics than in astrophysics. Right? And so one of the things they struggle with is, what is the utility of money? Is it its dollar value? And it usually isn't. Like for people, if you actually try to use this theory to study the behavior of people, larger values of money do not have utility that's proportional to the amount of money. If you have $1 million, you might not care about losing 10,000. If you have $1,000, you really care about losing 100, right? So there's that difference, and then so for understanding the lottery, there's also the fact that there's people gain some kind of entertainment benefit from it, and you want the utility to reflect that. But I agree with your premise, though, that playing the lottery is fundamentally an irrational decision from decision.
But it causes me to think about going back to the last question. Is that I don't know if you're familiar with working with the Palomar Transit Factory folks.
Yeah.
The time people need people. Ashish Mahaval and his group, they're doing these kind of calculations of what's the best next observation of a given transient to determine what it is. So it's not just the properties of the astrophysical properties of the observation, that is, it's a gamma ray burst or supernova or nova or a transiting planet or a microlensing event. What's the next best thing to nail that down? Well, what's the next best thing among the set of observatories that exist that I can use right now?
Right.
And so it's really a combination of observing facility and those capabilities, for example, spectroscopy or photometry or whatever, against the question that you need to have answered to best narrow down the class of objects.
So they're the
and
choice.
this is actually going to feed very deeply and heavily in, for example, the LSST project, where we're going to have 100,000 transients every night, that we just can't feed 100,000 emails to your inbox and hope that you will do some follow-up observation for us. We need to have some better, more realistic estimates of what are the next best things to do to really determine what this object is. So it'll be interesting to see your work connected to that.
Okay. Thank you for staying.
One question.
Just one more.
Is there in any way something in this methodology where you can identify false positives? Like something that looks like a orbit
right.
but it's not? And
Right. So
maybe
this
we're
is
showing
actually
entropy,
something.
or?
So this is something that I've wondered about, and I don't know any. So with that. So like one of the things that I worry about. Part of what I liked about this problem is that exoplanetary systems with radial velocity data, there's a model that's just outstandingly good. It's not, when we talk about this to statisticians, the reason people like Jim Berger and Merlees Clyde like to work on this is that, it's a place where parametric modeling is sound. In most of the world that statisticians work in, parametric models are really fictions, and so the fact that inferences in general, but Bayesian inferences in particular, are so conditional on the model, is a kind of conceptual issue. But here, we really know what orbits look like, especially if there's only one big planet. So the reason that this works so well here is because of that. But one can imagine settings where there can be unanticipated things, and my worry is, can you kind of get painted in a corner where, for the hypotheses you've chosen to account for, they'll force you to observe in places that will lead you away from serendipitous discoveries of things you haven't explicitly modeled. And I don't know what to do about that except have some kind of defensive model included among your options, kind of non-parametric. There might be something there I didn't anticipate and put that in. But that's a good question, what about the things you haven't explicitly?
Yeah, because I have explored this